In this lecture, we're going to discuss Lenz's law. Lenz's law is going to turn out to be a way to determine the direction of the induced current in the loop. And we are going to stick with clockwise and counterclockwise since we're dealing with closed loops, because that's the only way you can have current flow. The direction of any magnetic induction effect is such to oppose the cause of the effect. I often refer to this law as the law of status quo. So we learned in the prior section, Faraday's law, that the induced EMF is caused by a change in the magnetic flux. And the magnetic flux is calculated through this relationship here, where we have the magnetic field area and cosine of phi, where phi is the angle between normal to the loop and the direction of the magnetic field. Any of these can cause a change in magnetic flux, which then causes an induced EMF. Or we can say current through Ohm's law. And because we now have a current, and remember moving charge causes a magnetic field, that induced current is going to cause an induced magnetic field. And the direction of that magnetic field is going to be such that it returns the flux back to status quo. So if whatever you're varying in order to induce the current causes the flux to increase, the induced flux is going to be in the opposite direction or cause a decrease in order to return it back to its status quo flux. And if whatever is changing to induce the current causes the magnetic flux to decrease, the induced magnetic flux due to that induced current is going to increase. So let's look at an example of this because there's a lot of moving parts to take in. So imagine that we have a loop and it has an external field passing through it, and that magnetic field is increasing in strength. Not changing direction, the area of the loop is constant, but the magnetic field is increasing. That means that B induced needs to cause a decrease or be in the opposite direction. So that B total equals B external minus B induced, and so they balance each other out so that the increase in the external leads to a negative induced so that your B total remains constant. So they're behaving in the opposite direction. So the external field, remember the right-hand rule is that you grab the loop, so your fingers come out through the center, and your thumb is going to show you the direction of the current. So B external looks like it should cause a current in the counterclockwise direction. But remember, it needs to be negative or in the opposite direction, so we're going to flip our hand around and be in the opposite direction of the external field. So that actually causes a induced current that is clockwise. Alright, so on the next part of this video, I'm going to try to demonstrate to you this right-hand rule, because it is hard to imagine. So I'm holding here a paper loop with the intention of simulating the metal loop we're talking about in the example problem. So remember, we had an external field that was coming out of the board, so I'm grabbing the loop so my fingers are in the center of the loop, are coming out of the board, and so my thumb points in the counterclockwise direction. But because our magnetic field strength is increasing, we want, or what would be caused, would be an induced magnetic field in the opposite direction in order to maintain status quo. So I have to flip my hand around so that the induced field is in the opposite direction, so my fingers are going through the center of the loop, and that causes my thumb to point in the clockwise direction. So the induced current in this case would be in the clockwise direction. So your external field is always going to oppose whatever is happening to the magnetic flux. So if we have a scenario where the magnetic field is decreasing, then we would want the induced field to be in the same direction as the external field. Now, another way you can do these right-hand rule is to, instead of grabbing the loop, I always envision grabbing the loop, but that's what I learned originally, is a lot of students like to use the concept where if, say, our external field, or not our external field, our induced field is coming out of the board, you would put your thumb coming out of the board, and your fingers would curl counterclockwise. And if your induced field needed to be into the board, which always gets me in the trouble, then your thumb goes into the board and your fingers curl around clockwise. So whichever right-hand rule actually works for you, go ahead and use.